Hello everyone. In this session, we are briefly going to discuss about convolutional neural networks or convnets. And we'll also understand how they are different from the traditional multi-layer perceptron models that we already have learned. So while you are trying to solve this image classification or image recognition tasks, we simply can leverage the MLP models and try to solve them. Why do we need to use models like CNN in the first place? So that forms the subject of our discussion now. So what are the different disadvantages that MLP models has got and how CNN models are going to overcome them? Okay. So let us consider a particular simple grayscale image which is having an arbitrary shape of 3 by 3. So there are in total about 9 different pixels here. So typically you will have images of shape 720 by 960 or other dimensions. Okay. But I'm not going to consider this particular dimension for our illustration purposes. So I'm just considering a simple 3 by 3 image data here. In your MLP model implementation or in your MLP model building process, you generally do your data normalization first for your given image. So once you do data normalization, you basically flatten this complete data into a 1D tensor object like what you are observing here. So all of your 9 pixels are now represented in the form of a one-dimensional tensor. Okay, the first row now are nothing but the first 3 elements within your one-dimensional tensor. The second row are nothing but the subsequent 3 elements, and so on and so forth. This we are clearly aware of. So now every single pixel here is associated with a given input in your input layer of your MLP model. So every pixel is now an input within your input layer, which is represented as x1, x2, x3 and so on till x9. There are in total about 9 dimensions for your particular observation that you are having. So this is one observation, right? So this is one image that you are currently considering. For every image or for every observation, now you are having 9 dimensions associated with it. For an image of 720 by 960, you will have 720 multiplied by 960 number of dimensions then. Okay, I believe it's pretty much clear. So this is your input layer, this is your hidden layer H1, and let's consider an arbitrary size of 100. There are 100 different neurons associated with hidden layer H1. In a fully connected network, every single neuron within your hidden layer H1 basically receives all of these inputs. So all of these inputs are received by every single neuron here. Of course, there will be some weights associated with every connection here. Okay. So now in case of 720 by 960 images, so you have 720 multiplied by 960 number of inputs within your hidden layer, within your input layer. Then you multiply this with 100. So these many number of weights will be present for your hidden layer H1, because every single neuron within your hidden layer basically receives all of the inputs. So the number of inputs here will be 720 multiplied by 960. And then there will be 100 more biases that are associated with every neuron here. Okay. So there is a true explosion of number of model parameters for one given hidden layer within your MLP architecture, right? So the number of weights or learnable parameters here are truly unmanageable. So this is one of the biggest drawbacks of MLP. Whereas in case of CNNs, you just retain the original size and shape of your input data as is. You're not going to flatten that out. But later we'll also understand how there will be a reduction in number of model parameters in case of CNNs when compared to MLP. Okay. Let's proceed further in trying to understand what are the other disadvantages of MLPs. So the most common disadvantages is that MLP models are not translation invariant and spatial invariant. So to understand both these terminologies in a better manner, let's consider an example of image recognition task. You are trying to identify human face within a given image. Okay, so this is a particular human face. And now as part of MLP, you are just trying to flatten this particular image. The first row is now being represented here. The second row is basically represented subsequent to that. And obviously you know that the spatial information is lost in such case. And let's say that this particular image basically has this face on left hand side corner, top left hand side corner. Most of your train set images are having your face basically on top left hand side corner, and suddenly there is a particular test image with the human face appearing on bottom right hand side corner. Then your MLP model might not be able to recognize well. It's basically because the MLP model data, the trained data, has typically observed the face in the first part of your flattened array or flattened tensor here, and not this. In your convolutional neural nets, you basically have something called kernel or filter. So you basically use this particular filter and try to convolute onto this particular image. You just slide this particular filter for every convolution operation. For every operation that you are doing, you are trying to extract some feature out of it. So the subsequent convolution operation, you are extracting another feature. So obviously it doesn't matter if the face is here or if the face is here or if the face is here, it doesn't matter because you are going to apply the same filter over this particular image on and on again till you exhaust all the patches within the given image, right? So this particular problem is translational invariance. So this is addressed by CNN by convoluting the kernel or filter onto a given image. No matter where the position of the face is on the image, the CNN models will be able to recognize it because of its innate ability of convoluting a filter on the different patches within a given image. Okay. And what about spatial invariance? So this is spatial invariance, right? If there is a slight distortion in the face or some features of a particular human face, MLP might not be able to recognize. Let's say that instead of a face, you are now looking at digits. This is a digit 8, right? If there is a distortion in this particular digit, like let's say like it's written like this, it's written in a little tilted manner, then your MLP might not be able to recognize better, right? Because it's not preserving the spatial information, whereas your CNN models are preserving the spatial information. So all of these problems that MLP poses basically are addressed by CNN here. And this we have already dealt with. When you are considering an input image of 720 by 960, your weight matrix basically explodes. There will be 720 multiplied by 960 multiplied by 128 number of weights when your number of neurons in your hidden layer are 128. There will be 128 more biases that are associated. This true explosion of number of learnable parameters are typically addressed by CNNs. We will later understand on how much the reduction of number of model parameters is when you are using CNN models with the help of examples. Okay, cool. So in your MLP architecture, you had this hidden layer where you are trying to extract some features. So we always said that your hidden layers are responsible for feature extraction. And more hidden layers are present in your model architecture, then more and more complex features are being extracted from the given input data. So that's what we have learned earlier. But the feature extraction stage here typically involves both convolutional layer as well as hidden layer. Okay. So convolutional layer is basically helping us extract some features out of the given image. Let us say that we are looking at this particular image here. And this is a filter I was talking about. So this is a 3x3 filter or kernel that I was talking about. So you typically consider this particular filter and try to convolute upon this particular image. So this 3x3 matrix is now present on a particular patch within this particular image, right? You perform some mathematical operation by using both these matrices. This particular patch of the image has got some numeric data, and this filter also has got some numeric data. You perform some mathematical operation and extract a particular feature value out of it, or let's say that you extract a feature out of it. And in the next iteration, you basically slide your kernel by 1 pixel, right? I'm sliding the kernel by 1 pixel, and now I'm extracting another feature here. So likewise, you keep sliding your kernel to your subsequent row, and then you keep sliding your kernel to your subsequent row again till you exhaust all the patches within a given image, and you build something called feature map, right? In the whole process, by using this particular filter, you are trying to identify edges of this particular image. If you see, this right hand side image basically is showing us all the edges of this particular image. So one filter specializes in one feature extraction process. So this filter may be good at identifying the edges. Another filter might be good at identifying some objects or patterns, whatever it is. So depending on the kernel, you might extract different type of feature there. Okay. So this is what I was talking about. So the convolutional layer is also responsible for feature extraction along with hidden layer where you're trying to draw some complex aspects of your input data X, right? So now it's clear that both convolutional layer and hidden layer are responsible for feature selection or for feature extraction. And there are different filters or kernels that I have presented here in this particular slide. So this here is Prewitt operator, this is Sobel kernel, and this is Laplace operator. Right? So Previtt operator on horizontal direction, and this is on vertical direction. Sobel operator on horizontal and vertical directions, and this is a Laplace operator. As I have mentioned, these kernels extract different types of features. We'll have to choose our kernels wisely. So that's what I wanted to explain to you right now. And let us look at how the edge detection is possible in one of our subsequent sessions. Okay. But before we try and gain more knowledge on how edge detection is possible with Sobel kernel, let us actually try to understand the convolution operation that we are performing in convolutional layer. So how are we just sliding this particular filter on multiple patches of this particular image, and what are the different mathematical operations that we are performing, and how are we extracting the feature map out of it, forms the subject of our discussion in our next sessions. Okay, so that's pretty much all I wanted to discuss with you in this session, and thanks for watching.